a mishmash thing about, even though I don't have anything really clean or elegant to say about any of them. And the topic is, I initially said that I was going to give 3 lectures. One of them is going to be about like locating the information. The second was about trying to extract it and verify that you've extracted it correctly. In this lecture, I'm going to talk about the question of what do you do with the information, and so part of the question is, what do you want to do with the information? And I really like this discussion, an essay by Michael Nielsen, where he says, really thinking about what kinds of matter can we stabilize in principle? What kinds of interesting phases could exist out there? And that's really a question about designing matter. And when you're trying to design things, you ask how you can engineer a reality to fit what you want. And it's not really about what you can. It's not really so much about engineering as about what you want. So what kinds of states do you want to prepare? To some extent, the answer to that question comes from things like quantum computing, where certain states encode the answers to computationally difficult problems, but to some extent we're just limited by our imagination, right? And so what I want to do today is I want to talk about ways in which measurements give you sort of an additional like design principle, an additional tool in the toolbox that help you maybe generate interesting states, for whatever objective you might have in mind. So that's going to be the objective. So it's just this overall picture where Hilbert space is very big, and most of it's not only very big but very boring. There's a little corner of things out here. There's ground states, and we know a lot about them, and they're very interesting, but they're not sort of an exhaustive set of interesting states. And now there's also states that are defined in some sense by the mechanisms you might use to prepare them. So, for example, states that arise as steady states of distributive processes, or states that arise through sequentially generated circuits, which I'll maybe talk about later today. And most importantly, states that, or most relevantly to today's lecture, states you can generate using measurements and some kind of feedback based on the outcomes of the measurements. You can think about these. I mean, ground states obviously aren't mixed, but in general, in general, these could all be mixed states. They could be mixed states with topological order, mixed states with some kind of non-trivial entanglement structure. It's again, the question is very much what you want. And I must say, one of the difficulties I have in this entire space of problems is I don't really know what I want. Right, but maybe you do, and so this talk is going to be sort of really about, suppose, what are the constraints on like particular ways of generating states, and how do certain things like measurements and feedback help you get around these constraints? And again, this is a field where we don't know an awful lot, so I'm really just trying to present a few questions and a few simple results. Okay, so the questions I'm going to ask, I'm going to talk about measurements as components in finite depth quantum circuits. And I'm going to ask, what can they do? What can you do with a finite depth quantum circuit involving measurements that you can't do with a finite depth unitary circuit? So that's going to be one question. And then a second question I'm not going to say very much about because it's not something I really understand in a global way, is what kinds of steady states are possible. If you define a sort of a process that you can iterate over and over again that goes somewhere, what are the places to which it can go? And that's a question that I think I can say a few things about if you have questions, but I have very little that's concrete to say about that. And then there's this idea of I guess the third thing is a bit like the first thing. It's that you take a pre-existing quantum state and you measure some of it out, and then you do something based on those measurements. And so, what kinds of places can you end up when you do that? Okay, so that's the sort of question I'm going to ask. And so to set this up, I need to explain something that I think is going to be obvious to many of you, but I just want to make it visually obvious to everyone, which is the restriction, the nature of the restriction that comes from restricting yourself to finite depth operations with a unitary circuit or with an autonomous distributive process like a quantum channel or a Lindblad master equation. Again, just please stop me as I pass through, because okay, so this is sort of a very general diagram, but what I'm doing is so I have some state which I guess is a pure matrix product state, and you've probably seen some of these last week. So this is my MPS, and then what I'm going to do is I'm going to apply some to begin with some unitary gates to the MPS in this brickwork pattern. So it's a finite depth unitary circuit. And then I'm going to do something like, for example, measure a correlation between an operator over here and an operator over there. Okay. And I want to know what this correlation is. And so you know, how do I simplify the circuit? Well, one thing you can do is you can realize that for example, this unitary and that unitary are just connected to each other with nothing in between them, right? So you can cancel them out, and once you've done that, you realize this guy and that guy, and these two can also be canceled out, and so these unitaries, these U's can be crossed off against the U daggers, and when you do that, you realize that now the two operators are only connected in the circuit through the initial MPS. So you haven't really changed the correlations from the correlations of the initial MPS if your circuit is short depth and your operators are far apart. And in fact, if the MPS were a product state, there would be no connection at all, because I could just disconnect this part of the circuit from that part of the circuit completely. So I'd have no correlation at all. But even if I had some correlations to begin with, I'm not going to be able to change their structure at long distances, because I'm sort of not really, not really connecting the two operators at this finite depth. Okay, so this is a very general property of unitary circuits. You've probably seen it. It leads to the fact, for example, that operators grow inside light cones. It's related to the linear growth of entanglement and other phenomena like that under unitary dynamics. Now, the key point is that this also applies to quantum channels. And so, okay, what's the quantum channel? So we talked about it a bunch already. So you can think about it in this dilated way as you take your physical system of interest, you bring in an ancilla in the state 0, and then you apply a unitary evolution that entangles the system with the ancilla, and then you trace over the ancilla. And so that gives you this representation. So if you break this leg up, you get the Krauss representation of the channel. But yeah, so I don't want to do that right now. But yeah, okay. So if you take the Krauss representation of the channel, and yeah, I'm not allowing myself to do that. If you measure the ancillas and put the measurement apparatus inside the universe, or inside your system, then like Ehud said, that would be a channel, right? The key thing about a channel is that something always happens on every trajectory. So it's a trajectory plus a recipe for bringing that trajectory back into the reference form, as I'll discuss as we go on. But right now I'm defining a channel the usual way as a sum over Krauss operators, which I can equivalently write by dilating it in terms of introducing an ancilla and tracing the ancilla out. Okay, so the key point I want to make is the channel itself has this normalization constraint that just comes from the fact that the ancilla leg was normalized to 1. So there's unitary. The whole thing is a part of a unitary evolution of the bigger system. Now, okay, so maybe I should have written this to the blackboard, but I think it's easy enough to see that that if you want to evaluate some operator in the evolved state, it looks like this. So I can just write it out in terms of the Krauss form, and so if I do that, then I find that the operator evolution under the channel is given by this thing called the dual channel. right, which has the M daggers and M's in opposite, is sort of arranged differently than they would be when the channel is acting on the state. So that's the dual channel. It's a Heisenberg picture of the channel, and it's not as similar to the Heisenberg picture of, for a unitary evolution, it's just U's and U daggers, and you're moving them around. Who cares what's a U dagger and what's a U? But in the case of a channel, it does make a difference because, for example, this operator E star has no particular reason to preserve trace. The only thing that it's guaranteed to do in this instance is it's guaranteed to map the identity to the identity. So this is a bit of a mathematical aside, but the right way to think about states and operators and channels is that you can think about the channel as acting on the state, which is a vector, and the vector is a right vector, okay? And then the channel gets applied, and then what you do afterwards is you measure an operator, but the operator shows up on the other side of the circuit, so it's like a left vector. So an expectation value in a quantum channel takes this form where the observables live as left vectors, the states live as right vectors, and the operation, the left operation and the right operation of this matrix E, that's a superoperator, are in general quite different. They have different properties. So there's no reason why a channel would take a maximally mixed state to maximally mixed state in general. In fact, I can write down channels that don't do that, like spontaneous decay. But any channel takes the zero, the identity observable to the identity observable, and you can see that it has to do that because if I just imagine plugging the identity in here, then of course that's like observing. That's just like you contract the U's against the U dagger with the operator, which is the identity in between. And of course, that's just a contraction of a U and a U dagger between the left and the right halves of the circuit. And so that cancels, right? Yeah. Yeah. Yeah, let me go through this. Yeah. So yeah, exactly. Normally you'd insert a node. Let me do this more carefully. So here's my state. Yeah. That's a pure state. No, this is I haven't written the full state yet. This is the ket, let's say, of the state. It's a ket index of the state. And now I apply this unitary. I bring in the zero ket from the ancilla. I perform the trace. This is the ket side. This is the bra side, and you can see that these are the input legs. Those are the output legs. That's now a pure state. No, it's not pure state. It's this is if I connect it up, I can plug in a density matrix in here, right? I see. Yeah. So this is the thing you can do. I see. If you leave it open. Yeah. If you leave it open, you're saying there's two indices, right? This is a tensor. This is a tensor with two indices. Yeah. We can connect to a row because this is a bra type index and there's a ket type index, or the other way around, depending how you. Yeah. Exactly. Yep. And the key point is that density matrices is what you feed in at the bottom of these diagrams, right? And observables is what you feed in at the top of these diagrams. A very general procedure when you have a quantum channel evolution would be something like this. So I have a density matrix comes in the bottom, it undergoes its evolution, and then I measure something in the final state. It'd be helpful if you wrote it. Sure. I mean, yeah. What would you like me to write? So, okay. So let me take an input state rho in tensor 0, 0. Good so far. That's the bottom. That's the bottom of my diagram. And now I apply U and U dagger. Okay. Now I do a trace over ancilla. This is my output state. This is equal to rho out. That's the channel acting. It brings the out. That's the channel acting in the input state. It takes the input state and brings out an output state. Yeah. So if I no. So this is not. So yeah. So right now I haven't written it in transform yet. let me do that in a minute. So I just want to make I just want to complete the thought behind that diagram, which is now I compute trace of rho of the operator with rho out, right? That's what it means to compute the observable. Okay. And by the way, you already see that like the identity is special here because I just plug in the identity here, then I get trace of rho out is the same as trace of rho in because this is a channel. Yeah. Yeah. Yeah, there wasn't a no, and that's why this became trivially one, right? Okay, so if I wanted to write this out as a Krauss operator, what I would do is I would sort of instead of tracing it out like this, I would break this leg in some basis, and instead of performing the trace, I would explicitly write the trace as sum over some basis.
That means you've measured it in state K?
You've measured it in the basis K. Yeah, so the diagram I drew would correspond to getting the outcome K. Now I sum over possible outcomes, which is like taking a measurement, throwing out the measurement outcome. And that just corresponds to, instead of writing this trace, you just sort of apply specific bras to, and sum over those bras. Okay, so it's just a way of writing out the trace in some basis, which you can always do.
This thing that you wrote in the first line, right?
Yeah.
And is that already? It's not.
Yeah. So it's writable.
You do that or?
Yeah. Yeah. So it's like, okay. Right, that's that, and now each of these guys is if I by the way, notice that if I had a pure state going in, I just totally split this up into a bra side and a ket side evolution, and that would be a trajectory. And so this is a quantum channel in Krauss form. It's not unique because I could choose whatever basis I like to perform this trace in, but this is what a channel in Krauss form is. Okay. So, and this is of the form MK rho MK dagger, where MK can be figured out by rearranging objects in this.
But that object is still a mapping of rho in onto rho out. So but
yeah.
It's not a cross form.
This is just, I mean, this is notation. This is a channel. When you write a channel in Krauss form, it means that you write it out in terms of some explicit basis. That's what the jargon means. And it's helpful to do this because this form is a lot easier sometimes to manipulate than like this form. You can see that it's just like less symbols for one thing. So that's the point. And so you can think about this. I mean, so we like to write all this in this normal operator and super operator form, but you'd also think of writing it instead in terms of like it's a map from the algebra of matrices to the algebra of matrices. And so for the way this map acts, it looks like some kind of quantum generalization of a Markov chain or something. So it has some properties like column constraint, acting to the right, but the right action and the left action are totally different. Well, so the trace preservation is a bit like a generalization of the column constraint of a Markov chain where the columns add up to 1. So there's some constraints like that come from probability conservation, but those only the right action version of probability conservation is not left. It doesn't work when you apply the matrix to the left. So these matrices are very non-Hermitian, and so yeah, the Heisenberg evolution, the Schrödinger revolution is totally different.
And when you write sum on K with these in your figure,
yeah,
with the open K, that's the same as both.
Yeah, I'm literally just using the identity that this is equal to. Yeah. And these states aren't normalized, obviously. Yeah. Okay. So that's so the key point I want to make is just that the Heisenberg action of a channel is unital, which is say that it takes the identity to the identity. And so this is precisely the fact I need in order to generate light cones, right? So and to sort of draw light cones for channels, it's sort of helpful to introduce this notation, which is fairly common nowadays in the quantum information community. So in my original notation, I had evolution that's yeah, I seem to have deleted my lines. There's lines coming out of there and getting traced like that. So I don't know what happened to my trace, but that's just them there. Okay, so that's what I drew previously. But it's useful to combine the Bra and the Ket lines in just some kind of input line that's a super line, that's a density matrix coming in at the bottom and a density matrix going out of the top. Okay, and in that notation, what it means to trace the identity is now just some vector you put in on top, and I denote the identity vector by which is just sort of this trace without any operator by this circle on top. Okay, and so what it means for a channel to be unital in this diagrammatic notation is that if I apply a channel and then trace and then just apply and then measure the identity or observe the identity, it's like not applying the channel at all. So that's what light cone cancellation looks like in this notation for quantum channels, where each leg is a density matrix going in. Okay. So now I can play this game. I can apply that diagram to my circuit where I'm taking an initial. Now this notice is this is no longer an MPS, it's an MPO. It's the matrix product density operator because my legs coming out are all fat legs because I'm using legs to denote density matrix indices. And so now my identity to clean this up is the unital property, and I can apply that now once again. So for example, this guy, so on this pair of legs, it's pretty obvious that I can just apply that and delete the E. And I can just keep doing that until I disconnect the, except for the initial state correlations, I've sort of removed the E's that I faded out. And so that's the argument. Formally, the channels have light cones, and so a finite depth quantum channel that's local can't change the asymptotics of correlations. Okay, so that's a big constraint because you can't really. So you might have wanted to do something like take a trivial state to topological state at finite depth. But you can't really do that in the sort of, at least in the properties in naive density matrix properties, as you can see from this light cone argument. Okay, so that's so the boxes at the bottom are denoting the initial state. And I'm allowing the initial state to be a matrix product operator. If I didn't have the horizontal red line, then I would have a product density matrix. I'm not really insisting on that because it's not important, right? I mean, in some sense, if my correlations are funneled, if my correlations from here to there are funneled through here, well, this line was already there, and my initial states haven't really changed my correlations, and so it's still funneling them through the initial correlations that existed. So it's not just that uncorrelated states stay uncorrelated; it's that correlated states, a certain pattern of correlations don't change that pattern of correlations either. Yeah.
Is it a good reason to think that channels have light cones, that when you have a particular realization of cross operators,
yeah,
if you look at each of them, they might not have the same light.
Correct. Yeah, correct. I'll come back to that. That's obviously very important because if the Krauss maps had light cones, then life would be very different than it is. So Krauss maps don't have light cones, and if I didn't, this is why I wanted to have this diagrammatic argument, right? Because diagrammatic argument very clearly fails if you have a single Krauss map up there, right? Because it doesn't take the identity either going upwards or going downwards. Mm-hmm. All right. So that's a big restriction. So you might say, can you do things as quantum channels that you can't do as unitary maps? So this is a bit of a digression, but I just wanted to say it because it's sort of an interesting fact. So even though quantum channels cannot create non-trivial states at finite depth, they can sort of create, or you can embed non-trivial unitaries inside a quantum channel. And the simplest example of this is the following. So it turns out that if you wanted to have a unitary that translates every qubit in your system over by one site, there's a fairly simple proof that you cannot do that. There's a topological index associated with how many things on net you're moving across the system by one site at every time step. But you can get around this by just doubling the number of degrees of freedom you have. So you have a right mover and left mover, and you can make that happen. You can quite trivially make a translation operator in the right mover by essentially by applying a bunch of swap gates. And the point of this diagram is that this swap circuit acts precisely as the thing I wanted on the right movers. It does something else to left movers, but you don't care because you keep feeding in the left movers and pulling them out. They're not important. So you can have finite depth. So finite depth unitaries, there are finite depth objects that you can have in channels. There are finite depth topological features. I don't know how to quite define them in quantum channels that don't correspond to finite depth unitaries. All that you have is this general property that comes from the light cone. So there's this notion of a quantum. So someone should correct me if I'm butchering the terminology here, but you have quantum stellar automata, and the rules for these is that they take local operators to local operators. And in the conventional definition, they're also unitary. But they might not be local, they might not be realizable as local unitaries. The translation map is a good example of a quantum stellar automaton because translation just takes every operator to the operator one side over, right? It just moves the entire operator algebra over. So it certainly meets this definition, but it's not realizable as a finite depth unitary circuit. But then it sort of becomes okay if you add enough other copies and throw out the ancillas. Yeah. Yeah. Thank you. That's a great question. I don't know if it's true. I mean, if it's true that you can stack enough of them together to make something trivial, then it's true. If there's sort of completely irreducible QCAs that survive arbitrary amounts of stacking, then it's not. Then this construction won't work. But I'm not aware of any of what the actual status of results on that is. But yeah, so that's just one thing I wanted to say. So the non-trivial processes you can realize, even though you can't like convert short-range correlated, long-range correlated states. Yeah. 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 Yeah.
This way of thinking about it, just enlarge my space and think about and then go about.
I think that would not be a legal notion of a channel, because I think I don't want to allow for arbitrary patterns of entanglement in the ancillas that I'm pulling in and throwing out. But yeah, it's an interesting question as to whether one should enlarge one's notions to include that or not. But I think normally when I think about a channel, I think about sort of about a process where each ancilla comes in like some kind of very short range entangled or like totally unentangled state, not about a case where like the ancillas themselves are locked in state. That would be some kind of more generalized notion of a channel. Yeah.
Statement.
Hmm?
So what it proved is that the operator evolution is always unital.
Yeah.
but you could probe the state in some nonlinear properties, and that would still be non-trivial.
Absolutely, and that's what Ahud showed.
Right. So that the second part is not entirely true, right?
They're non-trivial states. I mean, the non-trivial states, they have like strange properties and they're like in their strange correlators, something like that. When I say non-trivial states, I really mean like states that like, yeah, states for which conventional linear observables and density matrix show anomalous asymptotics. Yeah, thank you. Yes. Many copies of, so yeah, so the point is that so the unitary that moves moves every site one step over to the right is non-trivial in the sense that it cannot be realized at finite depth. But the unitary that just moves all my A sites over to A sites and all my B sites over to B sites to the left, that is trivial because that's a swap circuit. So you can have something that's non-trivial for a single copy, but it's trivial for two copies. And so things like that, once you sort of relax unitarity to just this unitar channel concept, become realizable. Yeah. It is, yes. Yeah. Sorry, what are you asking?
This is another.
Yeah.
So maybe for terms of the operator.
Absolutely, yeah. No, I was making an argument for when these things are uncorrelated. So I used I just used sum upper bound, which is rigorous. Right. In fact, the operators spread slower than they have to in general. Okay. So that's what channels are restricted to do. And so yeah.
What's the difference between this ancillar and this tracing of the ancilla after you to get the channel and more general thing like an environment? Is ancilla acting like an environment?
Yeah, the ancilla is what we call the environment. Right. So it's a Markovian environment in the sense that, I mean, if you want to apply channels over and over again, each time you bring in a new environment, and then afterwards you trace it out and never see it again. So in that sense, this is a single step of a Markovian open system time evolution.
You don't mean there's no memory yet. You don't modify the environment.
Yeah, you don't modify the environment because you literally bring in a new environment each time step.
And when you say ancilla, do you really mean single qubit?
No. No. When I say ancilla, I don't mean anything in particular. Like it's sort of you know when you see it.
Well, sometimes
Yeah,
you really need.
Sometimes it happens to be a qubit. Sometimes it happens to be a qubit and have a specific ancilla. But in general, it's just some auxiliary Hilbert space that I bring in and entangle with my system to achieve some objective.
Often like we want the environment to be much larger than the system. So
Yeah.
That's what I'm getting at. I'm wondering whether to be a channel,
Yeah.
the ancilla that you brought in that vacuum.
Yeah. No, absolutely not.
Doesn't have
No, because it's a single step of evolution, right? It's not, when you say the environment's much bigger than the system, you're thinking about repeated interaction with the environment. And in this case, that is true, because after you've done this thing over and over again, each time you brought in a new ancilla at each space-time point. So after time t steps, So after t steps, your ancilla is definitely bigger than the system. That's also true, by the way, when you do more conventional things like influence functionals or whatever. The longer you evolve, the more degrees of freedom you can resolve in the environment. And so at short times, you don't really care the environment's big. Yeah. You need to make it at least, so if you see the way this trace works, you need at least as many of these things. No, because what you're constrained by if you take the Choi map perspective, is that you have your system, the ancilla, and then there's some Schmidt decomposition across this cut. and there's some Schmidt coefficients across this cut. And if you make this space much, much bigger, then you just decouple. So it doesn't buy you anything. Okay, so right, so now I want to talk about, so the reason I was banging on about light cones is that I want to now violate light cones, and I want to explain what it means to do that. And so I'm gonna, yeah, I should have been a bit more strategic. I'm gonna have to disconnect my iPad so I can see my notes. Okay, so let me, too complicated. It'll be fine. There's another board here. Fine. Okay, so yeah, go ahead. In that case, in the way I define, so you're thinking about, if I understand you correctly, you're thinking about a channel that does that. Yeah, in each qubit, right? I can just do it for single qubit now. And so the point is that now your state at the end is that it's the density matrix 0, 0, and so it has no correlations at all. So that's consistent with the light cone, right? You can sort of remove correlations. Yeah, I guess. Yeah, maybe I don't completely understand the question. Okay. Well, we can discuss later when we're I was once at a talk at Harvard when Bert Halpern was in the audience, and at some point he declared to the speaker, I don't know what you're talking about. You don't know what you're talking about. Let's move on. So okay, so the amazing thing for me was that after that the speaker went on. Okay, so now I'm going to do something that is going to appear illegal if you took me too seriously. But Ehud and I have both talked about this, and so we know it's legal. And this is quantum teleportation. Okay, so what I'm going to do right now is I'm going to take a bunch of initial states, a bunch of Bell pairs, and then I'm going to perform a bunch of Bell measurements. And so, by the way, is this notation clear to everyone? Okay, so I do a bunch of Bell measurements, and remember that the Bell measurement operators can be written in the same notation as Pauli's, like that. I don't know what equation to write.
You don't know what you got.
Right? Yeah, so okay, so this is some Pauli and this is some Pauli. So for example, let me give you an example. So the identity state is up plus, so you take the state that's up plus down up to normalization, right? And so this corresponds to fixing this leg to be the same as this leg. And the Pauli here correspondingly is the identity Pauli. If instead I had, for example, the X Pauli here, then that would correspond to up down plus down up, right? Yeah.
That's a way to write a projective measurement.
It's just a way to write a projective measurement in the Pauli base, but I just want to make sure that it's clear what these things, like Pauli operators, because it's going to be important. The fact you can bend these wires around is very important to understanding teleportation in an intuitive way. That's why I'm sort of dwelling on this. But is this construction, is this fact clear? It's just a fact about algebra, but okay. So now I do this. So I get, let's say, this is my outcome on this state. And then I get the outcome Y over here. And then I just get the identity outcome over here. And so now, if you follow this wire, you realize that this is like a bent version of a wire that seemed to take information from here to there while applying a bunch of 1-qubit gates. And so this is something that you can show at the level of just algebra, but it's much easier to see it at the level of these circuit diagrams, because otherwise you just have a lot of indices to sum over.
Why these 1-qubit gates?
The 1-qubit gates, because your wire looks like, right? This is your bent wire, and your bent wire only carries a qubit sideways instead of carrying it upwards. Okay, and now what you do in teleportation is okay. So if you didn't know what these outcomes were, you wouldn't know what to do, and you just have a channel. Because you're throwing out the outcomes, then you just have a maximally mixed state. But if you do know what the outcomes are, then you can say, let's say that what I want to do, let me say, okay, so it's helpful to find a target. Let's say the target is to create a state that's like a bell pair between, how many qubits do I have here? It's like, I don't know, call it n. So this is the state I want to generate, and maybe I don't care about the stuff I leave in the middle because it's junk. Right. So this is what I want to create, right? So what I've created in this run of the experiment, where I keep track of my measurement outcomes right now, is I have x times y is or I guess it's y times x acting on a state, which I don't know, z up to sine, and then what you do in order to fix it up and restore the initial state is, in this instance, you apply a unitary z, a rotation z at the target state, and then you get your reference bell state back out. Okay, and so this is the idea behind teleportation, and so the key thing about it is teleportation is not doing anything particularly, it's not doing anything nonlinear in the density matrix or anything like that. All it's doing is it's using your classical information in a very non-local way. Because using classical information from here and here and here all the way down the chain in order to decide what operation to act all the way on the right qubit.
Is this a channel?
It is a channel. Let me write it down as a channel, actually. So let me do that now, because that's sort of the point I want to make. So the channel, so corresponding channel. Whatever you want, really. I mean, so right, this channel is going to prepare a bell pair and a bunch of maximally mixed states. If I wanted to not have them be maximally mixed states, I would, for example, use this x outcome to say, aha, this guy's an x. And I would rotate it with x, and I would use this guy's y and rotate y and so on. So I clean it up everywhere and I have a bunch of bell pairs. Does that make sense? Yeah.
So if I replace these measurements by some like qubit measurement, I still write down the qubit measurement is from the operator, not x or something else.
Yeah, but I think that that would not really work for teleportation, because if your measurements are not rank 1, then you end up not having rank 1 projectors here, and then you're going to have like a triplet outcome is going to have a diagram that looks like that. And so that's not going to help you, because that's actually a channel acting sideways. So in order to teleport, you do need to have measurements with rank 1 outcomes, because you want these diagrams. You want your trajectories to have to sort of disconnect like this. See, they're actually arbitrarily many states, but they have to be rank 1. Okay, so let me write down this channel. Yeah, so let me, yes, the full channel looks like this. So I'm going to write down an individual term in the Krauss sum, and I'm going to sum over the Krauss map. So I get my sorry about the notation. So I get a let's say let me call so okay, here are my so it's 1, 2, 3, 4, 5, 6, 7, 8. So for example, here, I'm going to write down a particular sum in my series. Is like, for example, I'm going to project 6, 7 onto X, and then I'm going to project. I'm going to call this alpha, alpha 6, 7. And then this is going to be 4, 5, and then it's going to have some alpha 4, 5, etc. And then all the way down to when I've done all my measurements, and then I have a unitary operation, which is a function of all the alphas, and it acts on my 8th qubit in this example. Okay. So there's a bunch of stuff here. Then there's unitary at the end, and then okay. So now this is a Krauss map. So this is one. Yeah, this is a Krauss operator corresponding to the outcome. Let me give a different name. So it's A corresponding to the outcome, the vector of outcome. Okay, and the channel now is so the channel here is the key point I want to make is this is still most certainly a channel, but even though each alpha here is a product, and you might say, well, you know, it just looks like a bunch of local stuff. It's not actually local because the dependency of this final unitary on this entire series of measurement outcomes. So it's a sum of like products of local stuff, but you can't factor the sum into a bunch of into product of sums. And so this channel is sort of it's implementable by local operations, by local quantum operations, but it's not decomposable into local channels. So that's the thing that allows you to beat all the light cone bounds, because you just cannot write this as a local channel. Okay. So this, you can think about some of these as like, so there's a term of art for this, which is local operations and classical communication. And you can see that, you know, the local operations are in some sense doing what you might consider the heavy lifting, because they're the things that are giving rise to the entanglement pattern that you desire in the final state. But then the classical communication is absolutely necessary to clean up the final state into the form where you want it, in order to have a determinate final state at the end of the process, instead of just having a totally mixed density matrix. And the fact that classical communication is non-local is what allows you to beat the light cone bounds in the case where you're doing feedback in this way. Okay, so you're not doing anything quantumly non-local, but you're using local quantum operations to push entanglement around, and using the measurement outcomes to know which specific way you've pushed entanglement around. Okay, so that's. Well, if you didn't have the classical communication, you would just have maximally mixed state, right? Because there is sum over all these outcomes without the cleanup. Each trajectory you wouldn't, but then you'd have to post-select. So if you like, so with post-selection, you have no light cones in the first place, because in some sense, post-selection is like, it's like applying a non-local operation. It's not a unitary operation based on the non-local measurement record, but it's a reweighting operation based on the full measurement record. And so that's the thing that lets you, that's I guess how these things are connected. So yeah, indeed, you know, what's happening here in some sense, I mean, the way you do it in the diagrammatics, the way you see it in the equations is that on a trajectory, you get this entanglement, but then you sort of erase it with the randomness of the measurement outcomes being sort of randomness in the unitary, unless you do something to fix up, to de-randomize at the end. And that's non-local. Okay. Okay, so so let me just say that you can this is sort of the general principle behind quantum error correction, as Ehud discussed. So, for example, if you were trying to error correct the toric code, what you would have is let me draw this picture again. So you would have a bunch of these anyons. And so you'd want to connect them up in some way, and in order to connect them up, you'd have to take all your measurements that told you where the faulty measurement outcomes were. So an error terminated one of these points, but then you need to glue them together in some non-local way. And if you try to glue them together in a local way, you're not going to succeed in correcting errors. So that's quite general. And yeah, that seems to be necessary in the existing in most of the existing classical in most of the existing active error correction routines. There's an interesting question which I'm gonna comment on, but I don't really have anything intelligent to say about it. So if you had, could you do error correction with a decoder that was sort of only local, that only knew the local environment of each error, instead of a computer that gets fed the entire pattern of errors and has to correct them all at once, which is non-local in the way this is non-local. And so, as far as I know, the existing cases where this can be done are also cases where you can basically also passively correct the errors. So it's like you can just correct the errors by just cooling the system down. And so I don't know if it's hard to see if there's a deep connection between these two things. The cellular sort of these local decoders are going to have some kind of emergent light cone-like property, and so the question of how that ties into all of this stuff is an interesting one that I'm just going to flag as an open question that one should think about. You could ask this a similar question like in classical Markov chains. Can you have ordered phases in classical Markov chains that are local with local update rules that you wouldn't be able to have in equilibrium? So, for example, could you have ordering in one dimension? And the answer, rather surprisingly, is yes. But the simplest example of this phenomenon is in this paper that no one I know has actually successfully read by a guy named Gotch in the 1980s. So it's the explicit construction of a cellular automaton with a gazillion states per site, and some local update rule that he could prove actually did have a phase that was ordered. So yeah, it's an interesting phenomenon. We don't. Yeah. Local classical error correction, completely local classical error correction in a one-dimensional system. So the errors can get away from each other, but you can correct them passively. There's no non-local classical communication in Gotch. Gotch is a Markov chain. Like you just made up a bunch of local update rules. So yeah, this is an interesting phenomenon. I don't know what, if anything, it has to do with the quantum world, but it's an interesting phenomenon that one should have in mind, and thinking about what's the capacity of channels, how much non-locality do you need, do you need non-locality, and so on. So these are questions that seem very interesting and that we don't really understand much about. But so there are here are a few interesting leads on these questions. Okay. Any questions about this stuff? Because I'm gonna try and plug my tablet in again. Okay. So let me do that. Okay, so this is gonna suspense of whether it's gonna actually turn on. Oh, good. There we go. What did it do? Oh, good. Okay, so what I want to do now is is talk about this phenomenon that I introduced in the teleportation example of measurement-induced entanglement, and I guess connect it to a few more sort of interesting physical questions. So just to be clear, in the example where I did the teleportation, so I had, let's say, I had a region on the left, a region in the middle, and a region on the right. Okay, and and you can see that before I've made the measurement, it's pretty straightforward to convince yourself that there's no mutual information between A and B, because there are no bell pairs shared between A and B, right? So when you perform the trace over M, you lose everything. But now instead, if you measure A and if you measure all of M, then yes, I don't know why I have an extra bell measurement, but never mind that. But if you measure all of M, you can see that, just as I showed previously, you connect the singlets across this region, and now you have one bit of entanglement between the leftmost qubit on one side and the rightmost qubit on the other side. And so this object, this illustrates that when you perform measurements and condition on the measurement outcomes and measure the entanglement, condition the measurement outcomes, it can grow. You can't increase entanglement. You can't increase bipartite entanglement, but you can move entanglement from short range to long range by performing measurements. Okay, and so it would be kind of interesting to have a more satisfying mathematical handle on this. And so to talk about measurement-induced entanglement, I want to say something about open systems that maybe again is probably familiar to some of you, but I find it kind of helpful as a way of thinking about open systems. So this is an example where I have a quantum channel, and instead of calling the environment E, I'm going to call the environment Bob, just like I did yesterday for some reason. But so again, it takes a standard form. I extend it to unitary on a larger space, and then each time the ancilla that goes out remains out. It never comes back into the circuit. But I now have some state on the universe consisting of the system and the ancillas. Now, one way to think about this is a conventional way where you trace out the ancilla, and you get a diagram like that, which I drew previously on the board, and that represents the quantum channel, where I've removed the ancilla. I can also write it this way. Okay, I should have added the sum over K, so let me do that. The sum over K then gives you the Krauss form of the channel, where I take quantum trajectories where, conditional on the measurement outcome, I induce some evolution in Alice's space, and I sum over the possible things that I could have induced. Now, there's a third perspective on this, which you can think about as Bob collects the radiation coming out of this open system. So each time Alice and Bob interact, the qubit flies out, and Bob collects it and holds it in a safe for later use. And so let's say that Alice started out in some initial state, and we can say that Alice finished in some particular state. And so now, if you write this, if you look at this diagram and you turn it sideways, you'll see that what it is a description of a matrix product state. In fact, the matrix product state that's in canonical form, because you've probably heard this in Frank Polman's lectures. You can always put a matrix product state in canonical form, and the canonical form, I won't say anything about this. It's not important. Corresponds to the unital property or the trace preservation property of the channel. Okay, so now what I want to do is I want to say that I'm going to look at measurement-induced entanglement across a finite region in this MPS. And so what that basically means is that, what I'm going to do now is so I want to talk about entanglement between this region and that region over there, right? And you can see that the only way that those two regions are connected is via the black wire. That's the bond space of the MPS. And so if I wanted to measure out, if I wanted to generate correlations between these regions, they would have to flow through the thick bond space line. And if I perform a measurement on the ancilla that corresponds to projecting each of these guys onto, let's say, state K1, K2, K3, K4, etc., corresponding to measurement outcomes on that run of the experiment. So on that run of the experiment, what I've effectively done is I've been thinking, instead of thinking about measurement-induced entanglement, I can think about the spectrum of an iterated Krauss map, or the spectrum of product of Krauss maps. That's what measurement-induced entanglement is, and you can think about this. You can think about each, yeah. And so now if I wanted to think about the correlations between the left and between left and the right, if I one thing I could do is I could think about sending in a bell pair into the left end of this, just like because I want to talk about So I want to talk about the correlations between the input and the output. If I think about this MPS as a process moving this way, then I want to compute correlations between the input and the output, and I know how to do that because we've talked about it repeatedly in the past few lectures. In order to do that, you send in a bell pair into the input and ask how much how much entanglement survives between this guy and that guy after the Krauss maps have been applied in between. Okay. So the measurement-induced entanglement question for an MPS is basically a question about these about products of these transfer matrices. And this is not really restricted to one-dimensional MPSs. So in one dimension, if you just multiplied these transfer matrices, you'd eventually always, the sort of finite size matrices, and you take long enough products of them, and generically, you'll always end up with a projector onto one particular state. But even in one dimension, there are special examples of states for which this entanglement remains non-zero at arbitrarily late times, and the best example of these is the cluster state, the AKLT state, or some other SPT state that has some kind of non-trivial correlation. That has this property that if you measure out the region in between and the appropriate basis, these Krauss operators are effectively unitary. And so they don't degrade the entanglement between the input and the output. So that's a special feature in one dimension. It's fine tuning, and you need a resource state to do it. In two dimensions, you can play the same game. What you would want to do is in two dimensions, you would want to think about this sort of one row at a time. So I think about my transfer matrix. Raman drew some of these, and so it just has a bunch of physical legs coming out. But once again, it sort of has, you can think about it as having some connection between between these transfer matrices for individual layers, individual rows of my two-dimensional state. And I can ask the same question about the products of those transfer matrices. It turns out that these products do exhibit more interesting behavior. And the really interesting thing is that in two dimensions, so the transfer matrix is one-dimensional. There's an actual entanglement, there's an actual transition in the spectral structure of these products of transfer matrices, and this corresponds pretty much exactly to the random tensor network transition that Raman talked about. If you roughly can think about these objects, you can think about these objects as being made up of random tensors, and then you multiply a bunch of them, and so you can think about a Krauss operator as just like some generic random tensor, and when you measure all the tensors out, you create long-range entanglement. Okay, so that has some interesting implications. So you can use teleportation. So you can talk about teleporting information like I did over here. There's this also connects to things like, you know, if you took a pure initial state and you ran, so if you let me say this more precisely, because it's maybe interesting. So let me draw this two-dimensional random circuit again, just to remind you how it works. So so these sideways legs are bond space, the virtual legs, right? They're just connecting these tensors to each other to make the tensor network. In a tensor network that actually describes a state in 2 dimensions, you have physical legs that are coming out. And so this is what the state looks like. And before you've measured it, it's just some 2-dimensional state with area law entanglement and so on. And so what you do when you measure it is you fix these legs of the tensor. So in effect, you take these legs, you take these pink legs out of the game. And so then you just have a square, just have a square mat of tensors in 2 dimensions. And that's precisely, if you sort of stretch your imagination a bit and say these tensors are random, that's precisely the point that Roman was talking about when he's talking about transitions, the function of the thickness of these bond space lines in the size that as a function of the size of the tensors in 2 dimensions. And so in particular, for example, if you left the last row of these tensors completely unentangled, if you left them completely unmeasured, you measured absolutely everything else, then generically you would create a volume law state on this final time slice of the experiment, right? And so that's you might say, okay, that's a bit surprising because my initial state came from a short depth 2-dimensional circuit. So in some sense, it only had area law entanglement. But of course, there's no real paradox here because, like, you know, the area law in a higher dimension was very, you know, the area law in higher dimension is enough entanglement to give you volume law in a lower dimension, even if you don't create any new entanglement. Just pushing stuff around. You're pushing stuff around the way it all like accumulates at the end of the circuit. Yeah, those are the physical qubits. Oh yeah, sorry. It was last line, wasn't it? So there shouldn't be any going off to the right. Yeah, because the circuit ends here, and so yeah, the only legs coming out of here are the only physical legs, the only uncontracted legs lying in the circuit are the ones that are coming out at the end, and these describe a state that I created on the end qubits by measuring out the other qubits inside the system. And so you can see that, you know, I'm not creating entanglement and just pushing entanglement around, but I'm pushing it around in a rather surprisingly efficient way, because like I had area laws worth of entanglement across each of these cuts, and I've converted it into like a volume laws worth of entanglement in the state at the end. So there's actually an interpretation of this that's very appealing in terms of measurement-based quantum computation. So in measurement-based quantum computation, what you do something precisely like this, except you don't use a random circuit, use a 2-dimensional resource state like cluster state, which, okay, and we'll talk about why you want to do that. But so you use a 2-dimensional resource state like cluster state instead of a random tensor. But you play the same game. You measure each qubit, you measure physical qubits, and then conditional on the measurement outcomes of physical qubits, you perform measurements, perform new measurements, your next layer of physical qubits, and conditional those outcomes do something else and so on. But that's if you want to do a specific computation. But in effect, what you're doing here with the random circuit instead of proper resource state is just doing, you think about this as just implementing a random computation, and a random computation of like a reasonable amount of depth starting from a product state is going to leave you with a highly entangled state. And so that's how you want to think about the generation of this highly entangled state at the output layer of this system. Yeah, it's some non-unitary 1+1 evolution, but that's an important thing to note is that in the case where I use a cluster state, these tensors actually do have unitarity properties. So for example, and if I wanted to engineer a system where that was the case, I would have to create I would want to create an MPS or a tensor network in 2 dimensions that look like this, where each of these. So I'm going to call. Okay, let me make this guy pink. So each of these tensors has the form of it's got a pink leg coming out, and the pink leg I'm going to call K, and the tensor for this particular this tensor has the form UK, where UK is a unitary, and which unitary it is depends on what the measurement outcome was. So if I make my 2-dimensional tensor network out of tensors like this, which could be random otherwise, then if you like, that's a way of seeing this behavior, of understanding this behavior explicitly. Yeah, now it's a random unitary 1+1 dimensional circuit, and so now there's absolutely no question that it generates a high random state after a volt at long enough. Yeah, so in a non-unitary case, what happens is that if my circuit is thick enough, my matrices are so big that in a sense they're basically unitary. Because unitarity constraint barely constrains them at all, and so they're asymptotically unitary. And so you always end up in this situation. Yeah, exactly. Yeah, being deep in the volume law state. But by the way, these I can think about this case for real measurements instead of forced measurements as well, right? I mean, I'm just measuring the system, and I didn't really. Yeah, I mean, here I didn't draw measurement output legs, but they could have come out of the Bourne rule. I could have measured and kept the outcome of the Bourne rule. It's not important. So yeah, so you can think about these questions of measuring out much of a quantum state as a, you can think about it as a state that's being measured. You can think about it as some like instantiation of a sideways quantum process by doing it sideways like this. And so yeah, there've been many interesting works by Verica among others on like actually getting to the measurement induced phase transition, studying it, not using the conventional approach of 1+1 dimensional circuit, but by doing stuff with a 2-dimensional circuit using space-time duality. Okay, so of course the big problem with doing it this way is you've implemented a random process, but again, without the non-local feedback, you don't really know which random process you've implemented. You just get a different one in each trajectory, and it's not really clear what this buys you. And this is again the statement that if you trace over these measurement outcomes without and do nothing else, then you go back to talking about the standard correlation properties of the state, which don't do anything at finite depth. But if you keep the measurement outcomes, you're allowed to have a transition at finite depth. Okay, so I actually, I guess I should have let Ehud run over further, because I'm actually going to stop early because I've run out of things to say. We can have a discussion. Yeah, but there are lots of things that I wasn't planning to talk about because we don't really understand them well enough. But yeah, there's this general relationship between quantum states and lower dimensional processes, and a more general question of using measurements in the space-time dual way to prepare interesting states. Once you see that you can do this, you can also ask interesting questions about entanglement of quantum systems between different times or correlations how to think about mutual information between time slices at different times. You've already seen some things about this using the Choi map. Yeah, so I assume that all the channels we're talking about are Markovian. I was insisting upon that, but in fact, a quantum channel is just a specific, it's just, I insisted that each time I brought in a fresh qubit that hadn't seen any of the other qubits, but instead of doing that, I could have fed in an entangled state, like, for example, the bulk of a quantum Hall state, and that would give me some kind of non-Markovian generalization of a quantum channel. And that's a topic that people in quantum optics spent a lot of time thinking about in the 1990s, but sort of might be nice to revisit from this modern perspective. And yeah, one of the big questions that come out of this is a question that Ehud also raised, which is phase transitions can happen at finite depth. These are transitions that can happen in sort of peculiar nonlinear properties of quantum channels, or in processes that involve measurements and non-local feedback. Right? Our understanding of what a phase of matter is in light of this observation, because the way most of us always thought about phases of matter is you can't get from one to the other in finite time. But it's pretty clear now that if you allow for these new types of processes, that idea kind of breaks down. Like you can get from something to a qualitatively different something in finite time. And so whether you call that a phase or not is a bit semantic, but non-trivial changes in entanglement structure can happen at finite time. And so how does that fit into our understanding of phases of matter? Yeah, so that's all that I had to say. That's all I had prepared to say, but I'm happy to take questions. In one dimension, yes. There's a result by Piroli and Sarang that more or less says this. Any two one-dimensional somethings that are area law entangled can be connected at finite time. We don't know anything to speak of about the case of gapless states because we just don't have good enough representations of them to answer these questions. In higher dimensions, there's a belief that certain things cannot be connected to each other in finite time, and those are these non-abelian topological orders, which I am embarrassed at how little I know about them. But I mean, basically what happens in these cases is, what you do in order to do error correction is you start smushing anyons together. And what you'd like to do is you'd like for the anyons to fuse the identities and forget about them and keep going. Right, but in these non-abelian examples, the anyons just keep fusing to other anyons, and the process just doesn't really terminate in a nice way, and you need many different rounds of measurement and feedback in order to clean up the errors. So there seem to be things in higher dimensions that cannot be connected using measurements and feedback. So there is still some notion of what a phase is, but it's a much more constraining notion of what it means to be in a non-trivial phase. You'd also ask these questions about, suppose I don't allow arbitrary types of feedback and, put more constraints on things, would that give me anything new? But I mean, that's again, something that we don't really understand. It's related to these questions about how complicated does a decoder for a quantum error correcting code have to be? Yeah. So the statement is that any two MPSs, I guess any MPS can be converted to an MPS in two MPSs in generic different phases can be connected to each other in finite, using finite depth unitaries, measurements, and feedback. So the key thing is, I mean, I can go from one point in one phase to another point in another phase. It's got to be less entangled because I can't create entanglement through measurements, but I can. But there's always some point in the other phase that's less entangled. So I can. Yeah, I guess that's also true. Yeah, that's right. So thank you. Yes, but the finite depth unitaries allow you to crank up the entanglement to desired level, and once you've done that, you can just do measurements and feedback to clean up the state after. So that's what they showed. And strictly speaking, I think there's some factors of logarithms and the depth you have to go to, but it's like much, what's a log between friends? Yeah.
What you are talking about is for gap length systems?
Correct. I'm talking about MPSs at finite bond dimension. Yeah. So yeah, for gapless states, as usual, like much less is known. I'm not really sure what you. Yeah. Yeah. So deep thermalization. Thank you for that question. So okay, so what is deep thermalization? So the idea, it's actually quite closely related to this diagram. So maybe I'll leave this diagram up. Well. Yeah, I'm sorry. I'm not implementing feedback non-locally enough. So you have a state on let's say on n qubits, and I'm going to divide it into a region A and a region B. So the conventional understanding of thermalization is that it's the question of whether rho B goes to a thermal state, right? It's a question about whether a particular density matrix is thermal or not. Now, when you talk about deep thermalization, you're asking a slightly different question. What you're doing is you fix the measurement basis. Let's say you're only allowed measurements in Z. And by Z basis, I just mean the computational basis. You rank one measurement, the Z basis, and you measure out. So what you do for deep thermalization is you measure out A. So so when you measure out A, you get a pure state now in B, corresponding to the measurement outcome. So that's a pure state corresponding to these measurement outcomes, and so you get an ensemble of these guys. One for every measurement outcome, and of course they're associated with the probability. They're weighted by the probability of that particular measurement outcome having happened, right? So you can say, okay, what's the ensemble of the states? Are these states cover the system? They cover the state space uniformly and randomly, like the Haar measure on the state space. Okay. And you can see this is a stronger claim than just thermalization, because let's say that I had, for example, a single qubit. I can write two different types of ensembles that correspond to the same thermal state. One ensemble consists of half the time the qubit is up, and the other half the time the qubit is down. Right? This ensemble of pure states, when performing the average, gives me the mixed state. That's the identity density matrix. I could also have a pure state that was covering. I could have an ensemble of pure states each time I give you a new state that's sort of pointing in a random direction in the block sphere, and this would also give me the same density matrix, right? So these are two different ensembles of states that give you the same density matrix, and but it's meaningful to ask about the ensembles of states independent of the density matrix, and you can think about these, if you like, as higher moments of and so as higher moments of the distribution over states. Somehow the density matrix is the average over the states of the ensemble. The higher moments tell you something about about the coverage of the states of the ensemble, and deep thermalization corresponds to the ensemble becoming this ensemble of states becoming a random ensemble over the full state space. So it's a much stronger condition than thermalization. Of course, deep thermalization is not particularly easy to study experimentally because it has the same post-selection problem as everything else. Yeah. Deep thermalization is in principle, and yeah, it's stronger than ETH because ETH is purely a statement about what rho of B is. And the point is that rho of B can be a thermal state corresponding to a bunch of different ensembles. If you define an ensemble by this procedure. Yeah, so this is really a question about, what are the, so, why do I care about deep thermalization? Why does anyone care about deep thermalization? I mean, okay, the true answer is that people study deep thermalization because they compute things about it. It's sort of why we study anything we study. But the reason you might find it interesting is that it encodes sort of highly non-local correlations that might exist between the measurement outcomes, the set of measurement outcomes on left subsystem and whatever's happening in the right subsystem. So it's asking sort of stronger question than the regular thermalization question. Yeah.
If I understand correctly, you're saying so you measure the part system.
Yeah.
And I understand you're saying that this leftover pure state is perhaps very now complex, but it probably is like, let's say it's an exponential complex.
The leftover pure state has, it potentially has exponential complexity. If you define complexity through unitaries. Yeah. 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 Yeah.
So then question is, if I now go back to, if I think in terms of
Yeah.
if I just take the actual eigenstate of a Hamiltonian, without, I'm not doing any tracing
Yes.
or anything.
Yeah.
Not doing it a mixed state.
Yeah, take the actual eigenstate.
That's probably as complex. That's also exponentially complex.
The eigenstates of a Hamiltonian, though, don't. I mean, let's say a flow case system. So the eigenstates don't have any special labels. So each eigenstate is like totally random. So then you have an ensemble of eigenstates, and you can ask, is the ensemble of eigenstates the higher ensemble? And it's clearly not, because they have these orthogonality properties.
Yeah, that is, I was not
Yeah. Yeah.
complex.
Yeah.
Yeah.
Yeah. I agree.
That's kind of almost clear.
Yeah, so it could be, it could be exponentially complex without having the property of deep thermalization, though, because it could have correlations in it that when I measure out half the system, I'm still learning something non-trivial about the other half of the system. Yeah.
Sorry, take a product state.
Yeah.
Evolve for time.
Yeah. Yeah, precisely.
Then there's eigenstate. Then
Yeah, precisely.
Other two.
Yeah.
The eigenstates are
absolutely. Yeah. So thermalization, conventional thermalization happens fast, always. Deep thermalization, it only cares about subsystems, right? So deep thermalization of small subsystems happens like actually reasonably fast, because exponential, the complexity of the small system is still is an all-in-one number. So deep thermalization of small subsystems happens pretty fast as well. The construction of an eigenstate by, I don't know, doing phase estimation repeatedly or whatever is a much slower process, because it really cares about the full system. So that's, so indeed. So complexity is an interesting question, but I don't think it's like directly related to these properties of small subsystems. Yeah. Subsystem size. Because look, I mean, deep thermalization is a property of subsystems, right? So I have an ensemble of states. The ensemble is on B. That becomes a a discussion between you and whoever is trying to define deep thermalization. So, indeed, different moments in principle can thermalize increase at different rates. And you might assume that it turns out that that you approximately cover the entire state space in some well-defined sense. Like you fix a tolerance, And then to that tolerance, you dethermalize. All right, I think I've managed to exhaust questions, and so it's time for lunch.